Okay, friends of class 11th science, today we are going to start a new topic. This can be included in the topic of mathematics or physics, as well as it is a part of the chapter motion in a plane. Okay. And I'm going to start with this topic of vectors. Okay, this is the introductory part of what actually a vector is and how it is different from other physical quantities. So, first of all, let me tell you that any physical quantity is divided into two parts. One is a scalar quantity and the other is a vector quantity. What is scalar quantity? Something which is having a magnitude, that is a number only. And what is a vector quantity? It is having a magnitude plus it is having direction also. Okay, so if something is having only the magnitude, it is counted as scalar, and if something is having magnitude as well as direction, it is to be taken as a vector quantity. Now, which quantities do have directions? Which quantities are vector quantities? Suppose you have a block resting on a horizontal surface, okay, and if you apply force from one side, the displacement of this block will happen on this side. Okay, where does the displacement of block occurs? It occurs in the direction of force. Now suppose if you apply force from the opposite direction, the displacement of the block will also take place in opposite direction. So when you are actually studying motion of object, you also have to sometimes express the directions also. Okay, that is the importance of direction. There are a few examples in which you have used directions, such as these two physical quantities. One is distance and other is displacement. You know the difference of the two. I am not going into the deep explanation of what is distance and displacement, but you have been using this. And you know that in distance, direction does not matter. So distance becomes a scalar quantity. In displacement, both the magnitude and direction are required. So displacement becomes a vector quantity. So the quantities which are expressed by the use of directions, that means they have magnitude as well as directions, those quantities are said to be vector quantities. Okay, now few more examples of vector quantities. One is the speed. To express the speed, suppose I can write the speed as 40 meters per second. This becomes speed. Another quantity is velocity. What is velocity? If I simply write down 20 meters per second, this is not the velocity. Okay, then what is velocity? I have to mention the direction also. So I must write 20 meters per second east. or it could be west, or it could be southeast or northwest. Clear? So when I am expressing the magnitude as well as the direction, the quantity is vector quantity, and when only the magnitude is mentioned, the quantity is what? It is scalar quantity. Okay, that is a very basic difference between scalars and vectors. In very simple words, to distinguish between a vector and a scalar, you can say that vector has this and this, a scalar has only this. But this is not the entire story. The story of vectors is a very long one. Now, this was the difference between vectors and scalars many years ago. Then came one thing. Then came electric current. Electric current. How to categorize electric current, whether it's a scalar or whether it is a vector. Now, electric current has a magnitude. It could be 2 ampere, 5 ampere, 10 ampere. What is this? This is the magnitude. And electric current also has a direction. You know, whenever we draw a cell inside the circuit, we always take the direction of current as current emerges from the plus, the positive terminal, and current goes back into the negative terminal. But there have been some controversies. In the mathematics of vector, if the mathematics of vector, you will be learning it very soon. When the mathematics of vector are applied to electric current, it completely fails. That means electric current does not follow the rules of vector mathematics. Okay, so electric current is not categorized as vector, it is categorized as a scalar quantity. Now you would be wondering that if electric current has magnitude, it has a direction, then why it is a scalar? So we have added one more thing to this definition of vector, that is, to become a vector quantity, the quantity must have a magnitude, it must have a direction, plus it should also follow the rules of vector mathematics or the rules of vector algebra. So here comes the definition of vector quantity. Clear cut with this: any physical quantity which has a magnitude, which has a direction, and which follows the rules of vector algebra is said to be a vector quantity. If this is missing, the quantity becomes a scalar. If this is missing, the quantity again becomes a scalar. So if these three things are there, only then vector is the physical quantity is a vector quantity. One more example apart from electric current is pressure. Okay, what is pressure? See, if I press something like this, you will say that okay, pressure is being developed, and the pressure on this marker from my top hand is in the downward direction. Pressure on this marker from my bottom hand is in upward direction. This is pressure. So pressure has a direction. That means pressure must be a vector quantity. But again, it is not a vector quantity because pressure also does not follow the rules of vector algebra. Okay. Now, how do we represent a vector quantity algebraically and geometrically? See, if I write a number 2 meter per second, If I write simply a number, say 2, what is this 2? No direction, so this is a scalar. But if I write the same number 2 like this, that means it has magnitude, it has direction. So this becomes a vector quantity. We also represent vector quantities like this. If I put A, it's a scalar. If I put an arrow over it, it's a vector. This is also what? This is only B, and now this becomes vector B, vector C, vector K. Okay, so this is how we represent a vector quantity on the paper. How do we represent a vector quantity on a plane? So this is the plane or the reference frame. Do you know that all the motions are supposed to take place in a reference frame? So this is y-axis, this is x-axis. There is a point object which started its motion from this part, the starting point. This is the ending point. The motion took place like this. Okay, this is what? This is a vector quantity represented on a reference frame. The arrow is placed like this. So this is how we represent a vector quantity inside a plane. Similarly, if this is a three-dimensional plane, there would be a vector like this. This is a two-dimensional reference frame. So this is the vector. If it is a three-dimensional frame, then the z-axis would be coming out like this, and the vector would be somewhat like this. It would be half in the air. I cannot draw it. No one can actually draw it. Okay, this is how the vectors are represented. Now, the next thing is, how can we represent the directions? How can we represent the directions algebraically? So, we take the help of reference frame, y-axis, x-axis, and z-axis. Z-axis. Okay, let me show the z-axis. This is, suppose, the z-axis. See, if I move in this direction, I am moving in direction of x. If I move in this direction, I move in direction of y. And if I move outwards, I move in the direction of z. Z is not oblique, z is actually this. This is the drawing of z, but actually z is like this. Okay, now if I move in the direction one step towards x-axis, I call it as I cap. If I move one step in the direction of y-axis, I call it j cap. And if I move one step in the direction of z-axis, I call it k cap. So now I have three directions: I cap, j cap, and k cap. Once again, what is I cap? One step or unit step in direction of x-axis. J cap is one step or unit step in direction of y-axis, and k cap is unit step or one step in direction of z-axis. So these three are called the unit vectors. Mind the name. The name is unit vectors. Unit vectors, that means the magnitude of this vector is one. I said one step in direction of x-axis. One step. How many? One. If I move 100 steps in direction of x-axis, then I will write it as 100 I cap. If I moved one step in direction of y-axis, one step, then I will write it as j cap. If I move 3 steps in the direction of y-axis, 1, 2, 3, then I will call it as 3j cap. If I move 30 steps in direction of y-axis, I will call as 30j cap. Okay. Now if instead of moving upwards, I am moving downwards, that means I am moving like this. 1 step, 2 step, 3 step. 30 steps, if I am moving downwards, then I will show it as minus 30j cap. Okay. If I moved 2 steps outside 1 and 2, I will call it as 2k cap. If I moved 3 steps in outward direction, I will call it as 3k cap. Okay. Now if I moved 5 steps inside, not outside but 5 steps inside. Okay. 1, 2, 3, 4, 5. Inside I am moving how many steps? 5 steps. So I will call it as minus 5k cap. So these are unit vectors which are used for the representation of vectors in a 3-dimensional plane. Now if I say that I have moved 2 steps in direction of x-axis, then I moved 2 steps in direction of y-axis, and then I moved 1 step in direction of z-axis. So I will write this as 2 steps in direction of x-axis, 2 steps in direction of y-axis, 1 step in direction of z-axis, that will be 2 I cap plus 2 j cap plus 1 k cap. Clear? This is how I represent the vector quantity in algebraic form. Clear? So when you start reading the book, you will find something similar to this. Read the book, try to grasp the basic thing about this, and we'll meet again to discuss few more things about